Good afternoon and welcome to today's Intel Technology Provider webinar, Selling Intel Xeon Scalable Platforms versus AMD Epyc. I'm your host, Melissa Shaw, and before we begin, we do have a couple of brief announcements. This webinar will be available on demand for 1 year, and the Intel Technology Providers will be able to earn 5 training credits for your attendance today. Your colleagues can also earn 5 training credits towards your company's annual training requirements by logging into the Intel Learning Center to preview the on-demand version of this course and completing a brief quiz. Today's event will be interactive, so please disable any pop-up blockers that you might have installed. They can interfere with certain aspects of our web conference. And for an enhanced view of our presentation, click the black square that shows the Enlarge Slides button located on the gray bar above the slide window. And to download a PDF version of the slide presentation today, just click on the blue document icon that's located at the bottom of your console that's entitled Resource List. We encourage you to ask questions at any time. So to submit yours, please type it into the text box in the Q&A widget in the lower right-hand corner of your screen, and then hit the Submit button. We have 2 speakers today. Our first one is Jimmy Leon. He is our competitive analyst for the data center group. And then we also have Patrick Wong, who is our channel marketing manager. And with that, I will turn it on over to Jimmy.
Thank you, Melissa. Thank you for joining us today for our webinar. So we're going to get started with a polling question just to get us going. So get your mouse ready, and we're going to jump right into it. So we're going to start with the first question. Are you currently evaluating or selling AMD Epyc servers? So click yes or no, and I'll see how the audience responds. Okay, so looks like we are about roughly most of you, 50 to 40, 57% to 42%. So it's a good mix. Hopefully by the end of this training, you'll be kind of more informed about what our advantages are versus AMD Epyc. So I'm going to get started with a webinar. So there are key differences between our Xeon Scalable platform and AMD Epyc. First one is that we've been for a while, basically in a constant bit rate, basically, innovating, launching products. We've done it for the last 20 years, actually, in the data center group. Our current processor has over 110 world records, and you'll see them when I go over some of the performance slides. We do have a performance advantage on a per core basis, on a per node basis. And that's really important when, when you are evaluating a product, because basically having something that performs better allows you to buy, less servers and actually get your work done, with the least amount of server costs. The way our Xeon Scalable platform is architected is a little different from what, AMD Epyc is designed. So you can see in the picture on the right-hand side, you can see 4 dies basically in a package, which is the way AMD put together their server. Ours is basically a single monolithic die, and that actually is going to have a quite big difference on how the servers perform. We have ongoing ecosystem investments, so by the time a server kind of launches on the Intel side, we basically have gone through rigorous validation. We have, software engineers that have worked with ISVs and OSVs, basically validating software. We have enabled also kind of key features in our platforms. Whenever you hear, for example, AVX 512 on Skylake SP, right, that feature has been enabled in the industry by Intel and software engineers, right, kind of 2 years before the product ever shipped. So we actually try to make sure that customers have the best experience, out of the box whenever they get our platform. The way AMD Epyc designed their CPU, you can see since they have a multiple die, basically the cores, the caches, the memory are all spread across multiple die. So that does have a consequence on how the product is going to perform. One key advantage that we have, so if you are deploying into a virtualized infrastructure, if you have existing Intel servers in your server pool, you'll be able to basically live migrate between Intel servers, but you cannot do migrate AMD VMs between AMD VMs and Intel VMs. So that actually kind of increases the complexity of the infrastructure, which is going to drive up cost. One thing that we do try to provide here at Intel is sort of like a complete portfolio of products. So we try to address multiple verticals and multiple segments. So we have obviously compute products and a wide range of products. We have Xeon, Xeon 5, Atoms, Xeon Ds, and for different product lines. Storage products, SSDs, our Ethernet products, again, our software to make sure that you can get the maximum performance out of platforms. And then again, I want to reiterate our ecosystem investments, basically making sure that customers get a good experience whenever they kind of deploy our platforms. Again, we reiterate, key pillars for our products is proven innovation performance, the way we architect the products, and the way we enable the ecosystem. Basically, those are key pillars for us on how we approach, our Xeon Scalable platforms. In terms of ecosystem, I don't know if you heard of the Builders program, which basically creates architecture reference blueprints with different ecosystem partners to basically allow us to deploy our systems much faster and speed through solution deployments. So if you don't know anything about Builders, about the Builders program, I suggest you go to builders.intel.com, and you can see sort of just the range of companies and solutions that are being deployed and created with Intel Xeon Scalable platforms. Next, we're going to jump into basically the key differences between Intel Xeon and AMD Epyc. So key differentiations. So in the left-hand side, you can see Xeon Scalable is a single, fully integrated die. That means that all the cores, memory, caches, basically are laid out on a single die. On the AMD Epyc side, you can see that basically they use 4 dies to create a processor. They have basically the caches fragmented between the dies, so you can see they have 8 megs, so each of those dies has an 8 meg cache on it. In terms of how they connect the dies, right? They do what they use something called Infinity Fabric, which are basically links that connect the dies, and those are typically very slow compared to what we have on Xeon Scalable. You can see the bisectional bandwidth. We have about 768 gigabytes per second. Basically, if you were to slice the die in half, right, or the throughput between the two halves would be 768 gigabytes per second, right? If you do the same thing for Epyc, right, you have about 168 gigabytes per second, basically, and that makes a difference when you are transferring and sharing data between those dies. They do have an advantage on memory channels. They do have 8 memory channels total in the package, but those memory channels are basically split between each of those dies. So each die will have 2 memory channels. For Xeon Scalable, we have 6 memory channels total, right, and basically they all share among all the cores. And then they do have a speed limitation. If you want maximum speed, you basically have to sacrifice capacity because you have to go down to 1 DIMM per channel at higher speed. And then they do have an advantage on PCIe lanes. Those PCIe lanes, if you want more PCIe lanes, those are typically used for storage designs or GPU designs. But the majority of servers don't have actually enough I/O to basically pin out all that many lanes. So on a typical 2U or 1U server, you will not use all those lanes unless you're building a specific server or a system. I want to call out something that we do have in our platform, and that's kind of basically been integrated in the chipset moving forward of our products. And that's something called Quick Cat6 technology. Which basically allows you to offload cryptographic and compression functions of the CPU. So, for example, if you were to be using an encryption performance on a Xeon Scalable platform, right? If you're doing 100 gigabits per second of compression, right? That will basically eat up 8 Xeon Scalable processor cores. And that means that you're taking 8 cores away from value-added functions. For example, if you are internet host, right? If you are renting out VMs, that's 8 cores that you are not able to monetize. The same thing for cryptography, right? If you were to do cryptography, if you think of your iPhone, connecting to a server, right? All those connections, whenever you're streaming video, all those are encrypted, right? So you are eating up, for example, 54 cores. So that's more than a server if you're just doing cryptographic functions. So again, that's something that is unique to our platform, and it's something that basically AMD does not have on available in the platforms. I want to say a word about virtualization. So again, if you are deploying, Intel servers into a virtualized pool, basically all the migration between servers, between Intel servers is possible. So you can take a VM that's created on Skylake, migrate it back to a Broadwell and vice versa, right? On the AMD Epyc side, right, we are not able to do that. And it's basically because the underlying architectures are different. So AMD by itself actually does say that you cannot support migration between Epyc and Xeon processors. And again, the consequence of that is that if you are an IT person, right, you basically have to create a separate pool of AMD servers, that separate from the Intel servers. And if you want to migrate VMs, basically you have to create that isolated, or what we call an isolated compute silo of basically AMD servers and Intel servers. And actually it does create complexity for you in terms of having to manage multiple architectures. So next, we are going to go through some measure performance. So what we did before we introduced the section, we basically went and bought, an AMD Epyc server, and we ran it through different workloads to basically measure the performance of how it compares versus Xeon Scalable. But for that, I want to kind of have another questions. So what do you think? For similar performance, do you think AMD servers cost more or less than Intel servers? So go ahead and kind of click what your thoughts are. Wow, you're making my job easy. So the majority of you basically said that AMD costs, the AMD servers will cost, actually, never mind, AMD costs less. So actually you're going to make my job more difficult. And that's a myth that we're going to try to dispel during the rest of this presentation. So before I move on to performance, I want to explain sort of a concept that of the two architectures. When you evaluate a server, right? There's two ways of evaluating a server. One is you can look at benchmarks, and benchmarks serve as a proxy for what a real workload is. And in terms of the way we look at benchmarks and real workloads is, you can split them up basically in two categories. One is high NUMA optimization. And NUMA is basically having memory sort of next to your processor. It stands for non-unified memory architecture. So when you saw those 4 dies, basically each of those dies for AMD, they have memory next to it. Low NUMA optimization basically means that you have the whole memory in one block seen by the processor. For benchmarks, since people want to get the maximum performance out of a benchmark, they typically do NUMA optimization. So you can see if you're familiar with the spec benchmark, right? That's highly optimized for NUMA. Things like LIMPAC and Stream are optimized for NUMA. In contrast, the majority of workloads like web servers, packet processing, storage workloads, search, or database, those have a very low NUMA optimization. That means that basically the data will be spread out among all the memory and caches, and actually it's going to make a difference in the way that is accessed for AMD Epyc. So as an example, right, so when you look at published benchmarks, you can see that AMD has basically published basically 2 benchmarks, SpecN and SpecFP, and it's basically have not been publishing any other benchmarks. And the reason for that is that benchmarks like SpecN actually kind of favor the AMD architecture, again, because it's highly NUMA optimized, and basically having those multiple dies, they do not, they're not going to show any weaknesses on the architecture on that benchmark. There's some other benchmarks that actually will show some deficiencies on the architecture, and we kind of run some of those just to show you what it looks like. So whenever we look at the two architectures, so on the right-hand side we have the Intel Xeon Scalable. So you can see we basically have 2 sockets, right? If you are in this slide, we basically are showing the memory latencies on the dies. So if you are requesting data from, let's say, die socket 1 on the blue on the Xeon Scalable box, right? You want to access to that socket are at 129 nanoseconds. If you are local to the die, where you are in core 0 all the way to core 28, right, the access is going to be the same. It's roughly going to be about 80 nanoseconds. On the upper right corner, you can see the latencies across AMD Epyc. So if you are in the local die, basically you have 8 different dies. If you are in die 0, like accesses to that die are at 89 nanoseconds. If you go to anywhere across any of the other dies, right, your latency increases to about 140 nanoseconds. And if you cross the socket, right, your latency basically increases to around 240 nanoseconds or 200 nanoseconds if you are 1 hop away. So that actually does have a consequence in the way your service is going to respond and perform. So imagine if you had a workload, let's say a database, right? One day the data lies in socket on die 0. The next day the data is in die on die number 4 at the far right corner. So you can see you can get two different possible responses depending on where the data is. and that's basically is going to show us a performance variation and throughput performance for the workload. And for servers, right, that's the most important thing, basically consistency and being able to deliver sort of like the same answer over and over again. So that's one of the key things that people look for on whenever you're creating, service levels agreement or a service response. At the bottom, basically, this is a slide from AMD at the Linley Processor Conference. You can see just the variance of performance between NUMA-friendly and NUMA-unaware apps. So you can see the range of performance for them is between somewhere 127 gigabytes per second to 149 gigabytes per second per socket, right, depending where you are NUMA or non-NUMA optimized. So you can see that if you are non-NUMA optimized, which is the majority of workloads, right, you're probably going to get less performance out of the architecture than you would from an Intel Xeon Scalable platform. Performance per core is an important metric, and why is that? One is that it does allow you to, if you have still a lot of serial codes, and there's still a lot of serial code out there, it does allow you to deliver higher response times, versus having basically a weaker core. If you are licensing per core, an example of software license per core, like Windows Server, it's licensed per core nowadays, unless you have a site license. HPC codes, energy codes, some databases are licensed per core. So having a stronger core actually does allow you to maximize the return on investment on your of your software investment. Now, we also looked at enterprise and cloud workloads. So in here, we picked 3 processors. The first one is an Epyc 7601. That's their top beam processor. We chose 2-socket 8160, which basically has a slightly higher CPU price, but at a system level, it's basically equivalent on system price versus the 7601. And then our 8180 processor basically is our top bin part. So starting from the left, general purpose performance. So this is the spec FP and spec N. If I remember earlier in the presentation, I told you that basically those are sort of going to be the best benchmarks for AMD. Again, because those are highly NUMA optimized, so they're going to do well on the architecture. But towards the right-hand side, basically we move into more realistic application on workloads. For example, Java, right? Server-side Java, roughly equivalent performance, top bin 7601 versus an 8160, and if you go to our top bin, right, you get about a 27% increase. And the ones next to it are JavaScript and PHP runtime. Those are typically run by cloud service providers. For example, PHP runtime runs by, that's the front end for Facebook. They use a lot of PHP. Memory caching, that's basically when you are take an object. For example, if you think of Facebook, you have a picture and it gets pulled out several times, right? That's an example of a memory caching application. On that one, in this workload, you run out of network bandwidth before you run out of compute performance. So 8160 and 8180 sort of kind of performs at the same level. Packet forwarding, sort of like the same thing. You're basically taking inbound traffic in one NIC and then rerouting it to other NICs. So that's sort of like an example for a network-bound workload. Databases, that's where actually the weakest performance for AMD. And that's basically because you have a big, large data set that is sharing memory. and you have randomness. Basically, you are pulling data from different areas of memory, and if you remember all those different latencies between the dies, right? That's one of the key areas where having a unified cache, a unified memory does help, like we have in the for Intel Xeon. And then lastly is server virtualization. Basically, that's for just hosting VMs. So we do have an advantage, roughly about 37% a better performance for server virtualization versus AMD. Next, I'm going to walk through HPC workloads. So starting with, for this one, we chose, again, the top bin 7601. Then the 6148, which is actually a cheaper processor cost. That processor is roughly about $3,400 versus the $4,200 for the 7601. And then our 8160, again, similar system price versus the 7601. So starting from the left, stream, basically that just measures memory bandwidth, and it's NUMA optimized. So if you have 2 more memory channels versus Intel, right, you're probably going to get a little better benchmark on that. OpenFOAM, it is an application that is a computation fluid dynamics. It's open source. So that benchmark is basically not optimized for AVX. It's basically SSE. So they do have an advantage of that workload. And there's other CFD codes which we do much better, but we're still testing some of those. And then as you move to the right, Milk, it's a physics code, again, memory bandwidth bound. That particular code, if you were to run some of these codes, such as Milk, in a cluster environment, we actually do scale better and become parity after 2 nodes and kind of pull ahead after 4. So depending on if you are doing multiple nodes for HPC, right, single node would not necessarily kind of predict how your performance is going to be at a cluster level. And this is because if you have a network adapter in one of those remote dies, obviously you're going to go through multiple hops to basically get to multiple hops to get your data out, and that's going to create sort of variations on your performance. And I will show you an example of that for a network workload. And then moving to the right, NAMD, GROMACS, and LAMPS, those are examples of life science codes. Black-Scholes and Monte Carlo, those are examples of financial services. And then DGEM is an example of, sort of like applications that are heavily AVX optimized of, like LIMPAC. And again, for this chart, we basically gave sort of the best performance for Epyc. So we had a choice of compilers, GCC, the AMD Open Compiler, LLVM, and the Intel compiler. So basically we compile every application basically for the best compliant, and that's what we reported on this chart. Here's an example of how having multiple dies in respect to your I/O, how the AMD Epyc could perform. So what we did here is an example of packeted forwarding applications. So basically, you have an application running on the core where the NIC, on the cores where the NIC is located. So as an example, so on the top chart, you have the application running on socket 1, where basically you're getting 95 gigabits per second. If you were to run the same workload, let's say on the second socket, then you will be pulling about 84 gigabits per second, roughly out of the platform. If you were to do the same thing on AMD Epyc, right? If you have, the application running on that bottom left die, right? You'll be pulling about 80 gigabits per second out of that adapter, right? But if you were to run the same workload in any other cores that are in the same socket but different die, right, you'll be pulling about somewhere between 40 and 42 gigabytes per second. And if you were to go remote to the next socket, right, you'll be roughly drawing about 32 to 33 gigabits per second. So if you remember when I told you, on the HPC slide, whether at scale, whenever you're doing multiple nodes, you basically will have an InfiniBand adapter, where this 2 by 25 gig is. So as you scale your cluster for HPC, for example, right, you'll have basically this variance between nodes, right, and actually it's going to affect the performance of your applications. The next is an example of performance variation. Basically, what we did on this for this test, right, we basically ran two different workloads. So we took the server, ran it once for the memory caching application, then turn off the server, turn it back on, run it again, and we got a different answer, for each one of those runs. The variance for Intel was roughly about 2% across multiple runs, right? For that memory caching application, basically when you saw that, basically you have to cross all those chip boundaries to get to the NIC, right? You can see you get variations of performance. The variance on that was roughly about 36% run-to-run variation between runs. For a database application, again, what you have basically a big chunk of data in memory, right? And you are basically getting requests to multiple regions of memory. So each of those requests might hit different dies on the AMD architecture, right? You're roughly going to get a variance of up to 103% variance on that database just because of the multiple die architecture they have. And the variance for Intel for that particular workload was roughly about 2% run-to-run. So again, having those multiple dies for AMD actually kind of caused this behavior. So next we're going to jump, we're going to talk about performance per dollar. So I'm going to ask you this question. So if you have a fixed budget for a server, how would you spend your money? Would you spend more money on memory and less on the CPU, or would you spend more money on CPU or less on memory? I'll give you 3 seconds to answer. You will spend more money on memory, less on CPU. I'm kind of disappointed. Oh, bummer. So I want to address the sort of like the price performance and kind of when you first answer the question, which one do you expect will cost less? You got to look at the instead of pricing at a system level, and that's our best recommendation for competing versus AMD. So what I have here is basically a white box price sort of retail for a Supermicro system. So basically, I did identically configure, and what we did here is basically we went and picked each of the AMD SKUs and kind of find the one that had basically similar performance versus AMD. So let's take, for example, the top bin. There's an 8160 on the Intel side and the 7601 on the AMD side. So if you were to populate the system basically with 1 DIMM per channel, which is what basically is recommended for both Intel and AMD to basically get the maximum performance. If you populate less, obviously you're going to get less performance, more uneven performance if you in terms of memory bandwidth if you just do an unbalanced architecture. So again, $4,200 for the Intel CPU, $4,700 for the Intel CPU. But if you look at the basically the top line, so Intel will have 192 gigabytes per second. Epyc is going to have 256 gigabytes per second. So roughly the system's about the same price in terms of similar performance per dollar. But you'll argue, okay, so let's say if you want more memory on the Intel system, right? So you can see the price per gigabyte for Intel is roughly going to be slightly lower versus AMD. You'll get more memory, and obviously the system is going to cost more, right, versus AMD, but the price per gigabyte is about, roughly about the same across the board. So for every SKU that AMD has, basically there's roughly an equivalent system price system for Intel that can kind of match the performance of AMD. So there's no really overwhelming advantage on AMD for price performance. And again, if you were going to populate this with fewer DIMMs, having fewer DIMMs on AMD with less than one DIMM per channel for AMD, they actually is pretty catastrophic in terms of performance for AMD. And I'll refer you for memory in the backup that basically has the performance per channel population for both Intel and AMD. Again, so I'm going to close before I hand it up to Melissa. Again, completely different architecture direction for both Intel and AMD, right? Ours is basically designed for consistency and performance across a wider range of workloads, right? We do have, started a lot of systems and performance port records that we've launched, we set with Xeon Scalable. And just a reminder that we do have performance, leadership in many workloads at similar performance per dollar versus AMD. With that, I'm going to hand it up to Melissa for some housekeeping stuff, and then we'll close with some Q&A.
All right. So one of the things we do have going on this quarter is a promotion on the Intel Xeon Scalable processors. They are offering up to 1,315 points per unit for a maximum of 500,000 units as part of this promotion. So for some of the platinum SKUs, you can earn 3x the points up to 1,350, and on select Intel Xeon Gold processors, you can earn up to 450 points, and then you can earn 2x on select Intel Silver processors, up to 90 points, and our HPC and cloud data center specialists will earn 4x on select platinum and gold processors and 3x on select silver processors. So the link below does go to the local promotion that's happening in EMEA so that you can take advantage of that opportunity. And then we do have a couple of resources for you. We do have a page on the Intel technology provider website or section of the Intel.com site that talks about winning with Intel architecture. There are a number of key resources that provide insights from a competitive perspective. Additionally, we have a really nice sales guide that breaks out and gives you an overview of the key advantages of using an Intel platform, as well as giving you a SKU-by-SKU comparison from Intel versus AMD so that you can use that when you're looking to compare Intel and AMD products. And with that, let me turn it on over to Patrick for any questions and answers.
Yes, thank you, Melissa. No specific questions from our audience today, but I wanted to touch on two questions that are frequently asked that Jimmy can perhaps clarify and answer for us. Jimmy, the first question we typically get from a majority of the audience is a clarification on NUMA. You shared with us that NUMA is the workloads are typically NUMA optimized. When it comes to real world workloads, how come they aren't? Is it just the ecosystem hasn't caught up, or is this the inherent nature of those real world workloads?
Good question, Patrick. So if you think about NUMA, it's very difficult. It's very difficult to break out workloads to basically parallelize them or breaking up in pieces so they can be broken down and dispatched for to work on multiple CPUs. And that's why you've seen more typically for NUMA applications, you've seen HPC sort of kind of leads the way on basically being able to parallelize a workload and break it up in little pieces so you can go and break it down into multiple cores and processes. So for HPC, that's a little more common, being able to do NUMA optimized. But the drawback for AMD is obviously going to be that inter-socket, inter-die communication between dies, right? That is going to, even though they'll have good memory bandwidth performance, right, that performance is going to be diminished by basically that traffic communication between the dies and the sockets. As far as enterprise workloads, having those workloads that are not NUMA optimized, it's just basically the complexity of and the randomness of the workload. If you think of a database, right, you have databases that are huge amounts of data, right, and you are basically asking for data at random, right? So it may live in a different region of memory, in a different domain, basically in the platform, and that is going to be accessed at different levels or different latencies between each of the dies. So that's basically is going to cause some issues for an architecture like AMD, and that's why you've seen a lot of why the majority of servers out there, actually a majority of workloads out there, actually are optimized for 2 sockets, right? So those are for 2 sockets. For Intel, it's basically 2 NUMA domains, right? If you think about AMD, it's basically you are sort of having an 8-socket platform or 8 NUMA domains in a 2-socket CPU, right? And just the pure laws of parallelism, right, that things are not going to scale as well as you increase the number of nodes, right? It's just not possible, right? It's not physically possible, right? Things are going to scale from 1 to 2 to 2 to 4 linearly as you increase the number of nodes. And that's why, whenever they kind of stitch all these dies together, right, it's not performing as well as it could be with those multiple dies.
Thanks, Jimmy. And then the second one, which actually the audience did come in with the question, is related to the recent side channel analysis and side channel reportings. The question that came in and that we typically are getting asked is this information that you shared today prior or post the side channel updates and security issues that have arose that Intel is reporting on?
Yeah, so this is prior to the any patching or firmware or OS patching that will take place as a result of the side channel, side channel exploit, right? We do expect that we'll have to rerun these benchmarks again, but we are waiting for basically final firmware updates for Xeon Scalable, as well as if there's any patching on the OS, so we'll rerun this. As far as performance, there could be an impact performance in terms of depending on how the workload behaves. But again, this is going to depend on the workload. Typically for side channel, if you spend more time in the privileged space, i.e., if you do more I/O, right, your performance is going to be a little more impacted as you were just doing on just pure compute.
All right. Those are all the questions we had. Let me turn it back to you, Melissa.
All right. So that's all we have time for today. We do value your feedback, so please take a moment to respond to our exit poll that will appear when we close the end of the session today, or you can click on the survey widget that's at the bottom of your console to respond immediately. As a reminder, this webinar will be available on demand for 12 months. Please be sure to click the resources list widget that's at the bottom of your screen to browse additional resources that we've made available for you today that are related to this topic. And thank you for participating in our Intel Technology Provider webinar, and have a great day.